In this video, I'll show you how to graph a varying rate of change using a context of pouring water into a spherical flask. I'll play an animation showing a liquid being poured into a spherical flask. As you watch, think about the relationship between the height of the liquid and the volume of the liquid. Now would be a good moment to pause the video and try to make a graph of the liquid's height as a function of the volume added. Some students have already attempted sketches of this graph. Here are sketches of graphs that 4 different students created. Which one most closely resembles a graph of the water's height as a function of volume? I'll play the animation one more time. So which graph do you think is best? The answer is graph D. Let's think about why this is. We'll focus on how to graph height as a function of volume for the bottom half of the flask. Let's watch the animation one more time. This time the animation is going to stop after the water reaches halfway up the sphere. A blue line segment will also appear, and the length of this segment is going to represent the height of the liquid. I'll use the length of this blue line to represent the change in the height of the liquid. And this red arrow is going to represent the volume of the water that gets added to the flask. We'll start by copying the length of the red arrow onto the blue segment. So in both cases, the horizontal distance between each pair of black bars is showing the amount of change in volume. Now if we think about the amount of change in volume, we can see that when the bottle is half full, that delta H is roughly 3/4 as large as delta V. Let's rewind the animation. Now I'll show the flask filling up again. As the animation plays, think about how the volume of the liquid, the length of the red arrow, and the height of the liquid, the length of the blue line segment, are changing with respect to each other. To help us graph, let's split the amount of change in volume into 3 equal-sized parts. And now let's rotate the 3 segments corresponding to the changes in height. And this shows us that the height varies at a decreasing rate with respect to volume because for successive uniform changes in volume, the corresponding change in height decreases. Now let's make a graph. In this case, the initial height was 0. We can plot this point at the origin. The length of the red arrows would indicate horizontal changes on the graph. The length of the blue segment would indicate a corresponding vertical change on the graph. So now we have another point on the graph. Let's go ahead and plot the next 2 points. To get more points, let's make the amount of change in volume smaller. Note how volume has been divided into 6 uniform segments. And you can see that the vertical lengths of the blue line segments are large at first and then decrease for each successive change in volume. Let's rewind this. Now we'll map out the entire curve. Note how that even within the segments of volume, for small successive horizontal changes, the amount of vertical change becomes less and less. This curve is called an increasing concave down function. Now let's finish by thinking about the graph for the entire spherical flask. To produce this larger graph, we need to zoom. For the top half of the flask, as the flask narrows, for successive uniform changes in volume, the corresponding change in height increases. So height will vary at an increasing rate with respect to volume. So what do you think the rest of the graph will look like? Well, for successive horizontal changes, the amount of vertical change needs to become more and more. Let's take a look. So the rate of change of height with respect to volume changes from decreasing to increasing and produces an increasing graph that changes from concave down to concave up.